Our first speaker of the afternoon sessions is one of my favorite researchers in the field, Professor Pieter Abbeel. Pieter is a professor at the ECS department at the UC Berkeley. In addition, he is a co-founder of several well-known startups, such as Gradescope and covariant.ai. Pieter has done a lot of revolutionary robot learning research in the past decades. From his early work on acrobat helicopters to the laundry robot, and then to this new wave of deep reinforcement learning and meta learning, he has been presenting us some of the most elegant learning algorithms, as well as the mind-blowing robot experiments. If you are like me, doing research in interdisciplinary areas of learning, robotics, and perception these days, I'm sure you all always have to cite Pieter's works for multiple times when you are writing a new paper. So I'm super excited about this talk. And let's welcome Pieter.
Thank you, and good morning or afternoon or evening, wherever you are. So let me see if I can share my presentation screen here.
Yeah, and for attendees, if you're just joining our workshop, remember that to use the QA tool at the bottom of our Zoom interface to ask questions, and we have a raffle to give away gift cards for people who ask questions. And given the time limit, we'll take 1 or 2 questions after Pieter's talk. But if Pieter is available to stay a little longer, he can always reply questions in the Q&A tool, or he'll also be rejoining us in the panel discussions.
Sounds good. So the question I want to discuss in this presentation here is, when we do deep reinforcement learning, can we learn as efficiently from pixels as we can from state? And we started working on this project about 6-9 months ago. And this was our starting observation at the time. If you look at the learning curves, so vertical axis here is performance, the higher the better. Horizontal axis is amount of experience collected. If you look at these learning curves, what you see in blue is a learning curve where the reinforcement learning algorithm has access to state of the robot, whereas green, the algorithm only has access to pixels, what's on the screen. And this is a state of the art 6-9 months ago, showing a very clear gap in learning speed, depending on whether you learn from pixels than well from state. And so the question we're interested in is, well, does it have to really be such a big gap? Does there even have to be a gap at all? And if you look at this, I mean, ultimately the visuals here are not so complex. You can imagine that in principle, you should be able to learn as quickly from pixels as from state directly. So let's see if we can get there. So outline for this presentation, we'll first look a little bit at contrastive learning in computer vision, where it has been quite successful. And then I'll talk about 2 approaches of bringing that into reinforcement learning, 2 different angles of bringing in contrastive learning, and then we'll discuss. So contrastive learning in computer vision. If you look at the state of the art in computer vision, for many, many years, it was all pure supervised learning. But then as of 2019, the plot on the left shows that with a combination of supervised and unsupervised learning, it became possible to outperform pure supervised learning. And in fact, in the low data regime, horizontal axis here is amount of data collected, vertical axis is accuracy, so higher is better. In the low data regime, labeled data regime, complementing your supervised learning with, in this case, CPC, a specific type of contrastive learning, helps significantly. And then the more recent work from March 2020 called SimClear showed that as your model becomes bigger and bigger, which the horizontal axis on the right plot is model size, your performance can keep going up, suggesting that, especially in unsupervised learning, as you get larger neural nets, more data to absorb, you can keep improving performance, maybe indefinitely, at least as far as this plot goes. So the simplest version of contrastive learning, SimClear, goes as follows. You have an image, and you want to find an embedding of that image that's hopefully invariant to things that you would hope image embeddings to be invariant to. So you take your image, you have 2 hard-coded data augmentations of your image. On the left, a crop is generated. On the right, a recoloring, and there's a whole vocabulary of these hard-coded data augmentations you can apply to your incoming image. And then since both of these come from the same image, after embedding, they should be in agreement. They should be very close. So ZI and ZJ should be close. And then of course, there will be negative examples that should be far away from these embeddings. And so that's how you pre-train based on unsupervised data, an embedding of images that then hopefully can help you learn supervised a lot faster. In SimClear, it's done with a cosine inner product kind of loss, but you can also do this in other ways. The method we've been studying is essentially asking the question, can we do the same thing in reinforcement learning? So we have a replay buffer of data collected from previous rollouts. We could take data from that replay buffer, in this case, a stack of images, and then we could feed it, of course, along the top into the reinforcement learning losses for the actor, which tries to compute the value function. The actor tries to compute the policy, critic tries to compute the value function. And then along the bottom channel, there's an additional loss that is essentially doing SimClear. Augmented observations are generated, and if they come from the same original, they need to be close in embedding space. If they come from different originals, they should be far apart in embedding space. There are a couple of things you need to think about is, how do you generate your query key pairs? What's the similarity measure? What's the architecture to use? For query key pairs, we observed after extensive experimentation with many different data augmentation schemes that random crop worked best, and it's really all we needed. So that's what we did here. So both query and key are different random crops of the same original. Then to measure similarity, it turns out in the DeepMind control suite environments that we worked with, having a learned weight matrix for the inner product did matter, just experimentally determined that works better than just going directly with an unweighted inner product. And then third decision you have to make is when you do your encodings, whether or not to use momentum. There are these two thrusts in supervised/unsupervised learning. SimClear doesn't use momentum, and then Moko out of Kamingho's group at Facebook uses momentum. In our case, we found that momentum on the encoding of the keys actually matters for better learning, better signal extraction. You might think of it as stabilizing the learning process. So, what are the main results that we got here? Again, vertical axis is performance, horizontal axis is amount of data collected by the reinforcement learning agent, and we have a 4x4 grid here for 16 total different DeepMind control suite environments. And in gray, we have what happens when you run soft actor critic, one of the state-of-the-art RL algorithms on state, and in red when you run it on pixels. And so what you see here is that running on pixels with the supplementary contrastive loss works almost as well as running directly on state, bridging the gap almost entirely for most environments. A couple of exceptions, which we'll dive in more later, but for most environments, this bridges the gap. Rather than, so here we do a more extensive comparison if we average over, well, take medians over all environments, and in blue is after 100,000 steps, in red after 500,000 environment steps. We'll look at performance. First one is state-based soft actor critic, so full access to state. The approach we're presenting here, curl, is almost as good. Then Dreamer is a model-based RL approach. Traditionally, people believe that model-based RL should be more sample efficient than off-policy model-free RL, but we're seeing here that in this case, that's not true. Slack is a alternative model-free approach where the auxiliary loss is in terms of video prediction rather than the contrastive loss. Soft actor critic plus autoencoder is again a soft actor critic with a unsupervised loss, in this case autoencoder loss. Planet is another model-based RL method, and Pixel SAC is just running directly soft actor critic from pixels to policy and value function with no auxiliary losses. So it's clear the auxiliary losses help a lot and the contrastive loss helps the most. Here are some kind of final numbers for each of the environments at 500,000 steps and at 100,000 steps, which of these approaches has the highest score at that point, and it's more or less dominated by curl. We did the same comparison for Atari, which is not a robotics environment, obviously, but it's another standard environment to evaluate these kinds of algorithms in, and there's decision making there to learn to play a game. The comparison here, first column is human, then random. Human tends to do much better than random. Rainbow is the most effective prior model-free method. It's a Q-learning method from DeepMind. Efficient Rainbow is a more efficient version of Rainbow that came out later. Curl, which we present, is building on efficient Rainbow, adding the contrastive loss, showing that can most often help. And then simple is a model-based approach. And in this case, for Atari, we see that the model-based approach wins in about half the cases, and the curl approach and Rainbow in the other half of the cases. So now you might wonder, what are the most critical components in this setup? One of the things we looked at is, what are the environments where it struggled the most? And so Acrobot, Swing Up, Walker, and Fish environment from DeepMind Control Suite is where there is fundamentally a gap between soft-active critic from state in gray and doing curl, which is soft-active critic plus contrastive loss from pixels. And so this is even the case. You look at the bottom when we train for much, much longer pixel-based RL on these environments. So it seems like fundamentally there is something there maybe that doesn't allow us to extract enough information from pixels to solve the task. So we dug a little deeper into that, and so we set up a supervised learning problem where we collected data from successful state-based runs, then stored the image stacks from those runs, and then trained a supervised learner to see if it could predict state from this sequence of 4 frames. And we found that for the environments where pixel-based learning struggled, it was actually the case that even supervised learning could not succeed at extracting state from the images. So what that suggests is that in those scenarios, there's simply not enough information available in the pixels. You need access to other information that you just don't get from just pixel values. For example, in state, often there's contact forces that you have access to, which would be very hard to predict from pixels. And for some environments, it might not matter. For other environments, it might matter more, and that's where there's still a gap. Another thing we looked at is in the environments where curl is successful, what is it that matters? Is it going from a single frame to state that is effectively happening under the hood? Or is it that there's a stack of 3 or 4 frames that can help you get information out? And we see here in red better performance if you have access to all 4 frames, but it's actually not a very big gap. So it seems that largely what's being extracted by the representation learning is state information you can also get from a single image. Another question you could have is, well, it's all great to do representation learning in parallel with RL, but what if you have a data set ahead of time? That's maybe not that optimal, but it's still from the same environment. Can you do representation learning on that data set? And after you've done that, run RL on the learned representation. That is effectively representation learning without having access to the reward. And so what we did here is we set up the neural network such that only the representation learning backpropagates into the early layers of the network, and the RL loss can only be applied to what comes out of those early representation learning layers. And we see that actually there's not too much of a difference in performance. Red is regular curl with full backpropagation all the way to the image from RL and from representation learning, whereas green is detached and it's not as good. Sometimes it can't do as well, but often it's almost as good. Okay, so that was curl. One question we had after working on curl and seeing it work so well was, well, how much is coming from the contrastive learning versus how much is coming from the data augmentation aspect of it all? Because what we're doing is this cropping, which is putting information into the system that a cropped version of the same image has the same state under the hood in some sense. And maybe there's another way to extract that. So we thought, can we simplify this even more? And so in this work, we said, let's just do data augmentation. So we have rollouts. Then instead of just feeding the rollout images into the reinforcement learning algorithm, we do data augmentation and then feed it in. And there's some parallel work to ours called Dr. Q out of NYU that got very similar results, by the way. And the augmentations we used were crop, grayscale, cutout, flip, rotate, random conv, color jitter. And then we consistently apply those across the stack of frames that we consider the current state, which is 3 or 4 frames. We see actually is that this does really, really well and is even simpler. So it's very interesting here that you can just do data augmentation and get a lot of the benefit of representation learning and do RL from pixels that outperforms pretty much all the other approaches on almost all the games. There's just one game where Dreamer still wins, one environment where Dreamer still wins. With all the others, we have Rad and Curl getting the top scores. Here are some learning curves, again, comparing with state-based learning. And again, the reason we like to compare with state-based learning is because that in some sense seems like the gold standard. State is what we think of as the best summary of the situation of the world and the environment the agent is in. And so if you directly give it access to that, that should be really helpful compared to just getting images. And we see that state-based learning in gray, while of course very good, can be matched in most environments by RAD, which is just RL with data augmentation, or Curl, which is RL with data augmentation contrastive learning. We also did some ablations on which of these data augmentations matter the most. It's cropping that matters the most, and we did further studies on this actually, showing that within cropping, actually 2 effects are happening at the same time. When you crop, you reduce the amount of information you feed in, and you also randomly translate. And those are 2 different effects. Cropping, like reducing your view on things, as well as translating in things might not be as centered. It turns out that translation is the most important thing for this. And so even just translating things will have almost the same effect as cropping as data augmentation. And so what we're really learning here is translation invariance. Under the hood, when you look at the activations the network generates, you can see that without augmentation, sure, it does pick up on where the robot is, but only mildly so. Whereas with the data augmentation, and especially with cropping, you can see the neural network really zones in on where the robot is, passing that information on to the later layers, outputting controls. Okay, so we covered both Curl and RAD, 2 new methods to try to learn as efficiently from pixels as can be learned with state access. So how about these methods relative to each other? RAD matches and even slightly outperforms Curl, likely because it gets to focus on the task at hand. It doesn't have that contrastive loss. The only loss is the reinforcement learning loss. It's also simpler. So you might wonder, why ever bother with Curl if RAD is simpler and typically outperforms RAD typically outperforms Curl? Well, the reason you might still care about Curl is that it can be applied without a reward function. So as your agent is collecting data, and if you have no reward function available, you can run representation learning on the data that's collected, and then the learned representation can enable more efficient reinforcement learning once reward functions are made available. Also, if your task were to change, like in multitask learning, in Curl, you're not learning representation specific to any task. You're learning a representation to capture in some sense, the invariance of the environment relative to what comes into your pixels. So what's still missing in terms of possible future work? If we look at the ImageNet results, they look at Sinclair and MoCo, they look at static images. When you look at our results, RAD and curl, they look at a stack of frames, which effectively allows it to capture velocity, which is part of the state, of course, in robotics. But what it doesn't capture yet is behavior patterns. With a stack of 3 frames, there's nothing in the representation learned that might say, oh, maybe opening a door is a good idea, or climbing on top of some steps is a good idea. None of those representations are being learned. Those are much longer term temporal representations that are not captured at all with anything that I presented here, and that probably could help a lot, especially once you start thinking about representation learning for better exploration. When your agent goes into new environments, what are the kind of behaviors that you want to have internalized that might be very effective as you enter new environments? Okay, this was a bit of a whirlwind tour of representation learning to make learning from pixels as efficient as learning from state in, for now, somewhat simple but not super simple simulated environments. And the main direction we're looking at ourselves right now is to see how well we can also make this work on real robots. Thank you.
Thanks, Peter, for the great talk. We got several questions here. We only have time probably for 2. There are 2. First, there are like 2 related questions. So an anonymous attendee and Payam asked, why is translation environment so important for RL, assuming viewpoint is unchanged at test time? And what's the intuition behind translation being much more important than rotation?
Yeah, good question. So in RL, because there is gravity in these environments, you can't freely rotate things. So most of these environments are set up in a vertical plane. And so translation invariance, yes, but rotation invariance is just not a thing.
Cool. And the next question is from Georgia. Why does Atari performance not significantly improved with curl?
So very good question. I mean, there's 2 parts to that statement. So when we look at, does it significantly improve? We have to look at the last 2 columns, because curl here is applied on top of efficient rainbow, which is a highly optimized off-policy Q-learning method. And so we see that it actually usually improves, not always. So in that sense, I think there's a clear improvement that comes from it, even if it's not nearly as significant as we saw in the DeepMind control suite environments. Then there's another question: why does it not completely outperform model-based the way it did in the controls environments? That's something that would require more digging. The simple is a model-based approach and still wins out in about a little over half the environments. So there's something to be thought about there, why that might be happening. We don't have a full answer yet at this point.
Cool. Given that we still have 4 more minutes and there are so many people asking questions, let's take probably 1 more. Is that okay for Peter?
Of course, yeah. Mm-hmm.
This one from Yan Rudy. You mentioned state-based learning is used as a gold standard. What's your intuition on why pixel-based RAD and curl outperform state-based SAC on some tasks?
Yeah, that surprised us at first also. And then we realized that maybe you can do also data augmentation in state-based learning, and that we're not fully exploiting that in state-based learning. So it's not done as commonly maybe, but in principle, there are things you can do in state-based learning to also do data augmentation. And we're thinking, for example, the translation invariance that we're getting in learning from pixels, we're actually not infusing when we're learning from state. And so if we were to start infusing some of that in state-based learning, I'm thinking it would win on everything again, or I mean, it would be tied but not lose. But it's hard to know for sure. There's also a notion of priors, right? Sometimes a vision-based processing pipeline that has ConvNet architecture might have a better prior over how to process the incoming information than a fully connected multi-layer perceptron would have on a state-based representation. So it's worth thinking about. But my initial answer would be, I think if we are clever about data augmentation on state-based input, we can make sure it always matches again the data augmentation with vision-based input results.
Cool. I see there's still several high-level questions. And since Peter will be rejoining us at 4 p.m. in the panel discussions, moderated by Greg, so we are gonna save some of these questions and bring them to the panel discussions. And we will be excited to see you again at the 4 p.m. Let's thank Peter again.
Thank you. See you later.